What a doozy. Okay, guys, here we go. Let f and g be the functions defined by this and g be that. The functions f and g shown in the figure I put below, so it's down here, intersect at -2 and at b. And so we got those two guys marked up on our graph right here. It's really important for you to pause and take time to make sure you understand what all the numbers are in the context of a problem. Okay, so this is f and this is g. I know that f is got to be this top one and g is going to be this bottom one. Now, if you weren't sure, you can always throw this into your calculator because this one actually is a calculator problem. So I guess you can't always, only if it's a calculator problem. So this is what it looks like with a calculator. I went ahead and threw them in there into my graphing calculator, and then I hit graph. If your graph is all messed up, don't forget you can press zoom and then zoom 6, which will bring you to the standard window. If you want it to look more like, kind of like exactly like this one, we're going to have to change the window to go from -2 to 1 and probably -2 to 2 in our window, which you can find over here by just pressing window. So I'll go ahead and input those in here. I went ahead and used -2 to 2 and -2 to 2. So now let's see how that changes my graph. Now my graph looks more like what I see when I'm looking at the problem right here. And that's what you guys are looking at on your FRQ. So let's get on with the first question. It says, find the area of the region enclosed by the graphs of f and g. Area is the calculus word that we're looking at right here. And you guys know that concept. To find the area between two curves, you have to subtract the curves inside of an integral. So this is what it looks like. Here's A. We're going to write, well, I actually like to define my functions because that way I don't get confused between the y1 and y2. And so I plug those into my graphing calculator into the y1 and y2. So I know that these are how they're related and how I'm going to plug them in. Whoa, those words made no sense. And then I'm going to find the integral between -2 and b. And so that's what I wrote out right here. I just went ahead and wrote capital B. That's what they defined that x to be. And I subtracted my two curves. Now you notice that I use y1 and y2, and that's okay because I redefined the natural log function and the polynomial, the x to the fourth function as y1 and y2. You don't have to do that. You can still use f and g if you want, but I don't recommend writing out the functions. While that is correct, there is a chance you might make a mistake. Like for example, this one right here, the g, it has x to the fourth plus 2x to the third, and you're supposed to subtract that. If you don't put parentheses around this, or if you don't distribute that negative properly, then you're going to lose a point for using that. So anyways, this, in other words, here, let me show you guys what the mistake would be. You could write natural log of x plus 3, and then minus, where'd that line come from? And then minus, what would that be? X to the fourth plus 2x to the third. And if you don't put these parentheses, that means the negative is not going to get to that 2x. So if you put this into your integrand like that, you're going to lose a point for that, which would be kind of a huge bummer. So make sure you don't make simple mistakes like that. And the easy way around that to make sure you don't is just to use the labels that they give you. You'll also be able to write less. Okay, so now let's find this b. In order to find this b, we have to find the point of intersection of these two curves. In order to do that, I'm going to go back to my graphing calculator, and I'm going to use second calc and then intersect. That's 5. Do not just drag the cursor across the curve. You will not get an exact answer. You want to use that function that you can find at 5 under calc. So what I'm going to do here is select the first curve just by pressing enter. And then it says, what's your second curve? Well, that's my second curve. I actually only have 2 curves, so I say enter, and then it wants to know where I want it to guess. I want it to guess close to that point of intersection because I don't want this point of intersection because I don't want it to give me that answer. So I just have to make sure this cursor is closest to that one. And it looks like it is closest to that one right now. I don't really have to move this over at all. But I could if I wanted to, or I can press a number like 1, and that would make the cursor go way over here. But then I just press enter. I get my point of intersection as 0.782. And so I'm going to write that in right here, 0.782. And now I just plug this guy into my graphing calculator. And so it looks like this. So I'm going to go back to my home by pressing second and then quit. Now I'm going to go math and then 9. So I get my integral. I'm going to go from -2. Make sure you use the negative button. And my other number was 0.782. And then inside my integrand, I want to put my two functions. I said y1 minus y2. So I press vars, go to y vars function, y1 minus, and then I'm going to go to vars again, y vars function, and then y2. And then I just have to throw the x into the constant thing right there. And then booyah, I get my answer. 3.604 is my area. Okay, so I go ahead and box that sucker and I'm done. Well, actually, I didn't even box it. Okay, here, I can box it. Boom. Okay, next, B. Now, when reading B, it says for the interval, we're familiar with that. We know what that means. Let H be the vertical distance between the graphs of F and G. So the vertical distance would look something like this. I would go this point minus this point. And that would be true for any other 2 points on this graph. Of course, these points have to have the same x value. But all you're doing is you're subtracting the top curve minus the bottom curve. Okay, and that's our calculus concept right here. No, actually, that's not our calculus concept, but we do need to know how to find the vertical distance between two graphs. It says H is increasing. Is H increasing or decreasing at x equals -5? There's your calculus concept. We have increasing and decreasing. I actually have to do two boxes because they're on separate lines. But in order to know if a function like H is increasing or decreasing, we need to know what the derivative is, what the slope is at the point that they give us. And so let's go ahead and write out the function h equals f minus g, and now let's find the derivative of h. The cool part is you don't actually have to find the derivative of h because this is a calculator problem. We could just throw this into our calculator. So let's go ahead and do that. Once you're in your calculator, hit math and then hit 8. 8 is the end deriv. Okay, and so my function or my calculator has math print, so it looks like that. I press X, and then inside here, I want to put y1 minus y2. So I'm going to go vars, y vars, function 1, minus vars, y vars, function 2. And I want to find this derivative at -0.5. And then I press enter, and I get my answer. You might have noticed that my numbers are already rounded to 3 decimal places, and that's because in mode, I made the float right here be 3. So it just rounds for me. I don't have to worry about the rounding. It's dangerous, though, if you do that, because the number's rounded. So you got to make sure that you remember that the number's rounded. And I'll show you guys what I mean later. And so let's write this out. We got our answer right there. So what does that mean? That means because h prime is less than 0, it's a negative, h is decreasing at x equals -5. And that answer is done. Okay, let's go over to C. The region enclosed by the graph of f and g is the base of a solid. Ooh, we have a volume formula coming up. Cross sections of a solid taken perpendicular to the x-axis are squares. So because we're perpendicular to the x-axis, our integral is going to be with respect to x. Find the volume of the solid. There's your calculus concept. Find the volume. So I'm going to box that really fast, the volume. And to do this, we're going to use cross sections. They give us the cross section right here. Let's write our integral out first. This is kind of like our formula. We are perpendicular to the x-axis, so we need to write an integral that is with respect to x. Our area function for the cross sections has to be with respect to x. And our two limits, the -2 and the b, have to be x's. Okay, so now let's talk about our area function. It is a square, and so that would be side squared. Okay, but we can't have s. We have to write area in terms of x. And so S would be the distance from the top function to the bottom function. That would be the distance right there. And so you just go f of x minus g of x squared. Now, just to help you guys see it, this is S and my square is popping off the page like so. Okay, and the sides of the squares are dependent, like the height of the square is dependent on the length of the distance between the 2 points. That's because it's a square. All the sides are supposed to be equal because it's a square. Okay, so back to this guy over here. Now I'm going to plug this guy into my integral, and then I'm going to just punch it out in my graphing calculator, which is great. I love my graphing calculator. So we have to go y1 minus y2 and square it. All right, look at my little trick here. I'm going to go, let's go back to our home. So second quit. I'm going to go up and just copy this guy by pressing enter. And then I'm going to put some parentheses around my y1 minus y2 so that I can square it. Now, so it doesn't write over that, I have to insert. So I'm going to press second, insert, and then open parenthesis. Now I have my parentheses around the y1 minus y2, and then I'm going to put squared on those guys, and now I just have to hit enter. I don't have to put in the new b because it's already there, or the b, it's not a new b. The answer is 5.340. So let's go over here and put our answer, 5.340. All right, that one's done. Last one. Now this one threw me for a loop, guys. This one's crazy. So pay attention. We have to identify our calc concept so we can actually do it. The vertical line in the XY plane travels from left to right along the base of the solid described in part C. And so this line right here is actually going to be traveling, starting over here, I guess, and going from left to right. I think I drew another vertical line, yeah. And it tells us that the vertical line is moving at a constant rate of 7 units per second. I'm honestly not sure how we're going to use this yet, but as we're going, actually I probably shouldn't put the line outside of the curve, but anyways, it's like it's in there, and it's moving at 7 units per second. So we're going this way. Whoops. We're going this way at 7 units per second. Whoa. Okay, so as it's moving across, that means our square is going to be changing sizes as it's going across. See this square right here? It's going to be smaller here, and it's going to be much bigger right here because the distance is bigger. And it says right here, find the rate of change of the area. There's our calculus concept. We got to find a rate of change. So find a rate of change of the area. Actually, I could just circle or box rate of change because that's all we need. Of the cross section above the vertical line with respect to time when the vertical line is at position x equals negative 0.5. Whoa, this is so much. So we're going to find a rate of change at negative 0.5. That means we're going to find an instantaneous rate of change. But in order to do this, we first need to have a function so that we can find its derivative, so we can find out the rate of change. And so our function is the area function that we found earlier from part C. All right, this guy. So I'm writing that out. Now, if I want to take the derivative of this, remember that this is a time thing. We're dealing with related rates. You have to take the derivative with respect to t. And so I'm going to go ahead and write that out. I'm going to take the derivative of my area function with respect to t. Now, this gets kind of crazy here. First, let's start with this side. When I take the derivative of a, that would be either a prime or dA over dt. But then you have to multiply this by dx over dt. Why? Now, this is kind of weird because a is a function of x. All right, that's kind of weird. And in fact, I wouldn't have thought of this right away. And what I actually thought of is taking the derivative of the other side. And so if I took the derivative of this side, that would mean I have to use the chain rule because I have these to subtracting and I have a squared right there. And so I put the squared down here and then I write the inside and then I had to multiply it by the derivative of the inside. And when I do that, I get this. It's a lot more to write And you'll see when I took the derivative of the natural log of x plus 3, I have to multiply it by dx because we're taking the derivative with respect to t and not x. Over here, I went ahead and distributed this negative, and I got negative 4x to the third dx dt and negative 6x squared dx dt. Whoa. Now, I had to find what dA dt, or what this rate actually is at negative 0.5. So there's two ways to go about do this. I could plug in negative 0.5 into here, into here, into here, into here, here, and here, into all my x's. But then what the heck is this dx dt? What is that? So I kind of got stuck here for a second, and then I remembered this 7. I haven't even used this 7 yet. Could this 7 be dx dt? Is that the rate at which the x is changing? Yes, because this vertical line is moving from left to right. That is the dx dt. And so that's, you can just plug 7 into these dx dt's and it works. Now, back to this side. Because I looked at this and I thought this side equals this side. So I can deal with this big ugliness over here, or I can deal with this pretty thing over here. Now, you might not understand this side. So if you don't understand this side, then this is the side you want to hang out at and just plug in all the right numbers. You'll get the same answer. But I'm going to hang out over here because dA dt is A prime. So I'm going to use this. I want to say A prime of negative 0.5, and then I have to multiply that by the dx dt, which we know to be 7. And so that actually works out pretty nicely. I'm going to go ahead and plug this in my calculator. When I do that, let's see, that's what my calculator looks like. I need the dA dt. I need to find the derivative of the ax, and ax is y1 minus y2 and then I gotta square it, and I want to take the derivative of this. Oh shoot, I should have wrote the derivative first. Actually, it looks like I have that right up top, so actually, I could make a quick shortcut here. So I'm gonna go up here and copy this, and then I just got to put the squared around the y1 minus y2. So right here I have to go second insert, and then I could put my parenthesis, then I got to move it over, and then I got to put another closed parenthesis squared. Cool. And I'm going to take that and I'm going to multiply this by 7. Okay. You want to make sure you have this whole thing right here and then multiply that by 7. Don't take this guy and multiply it by 7 because this guy is rounded. You got to take this one. Okay, and then the calculator won't round it until after it multiplies it by 7. So I hit enter. I get my answer as negative 9.272. And so for over here, I'm going to put negative 9.272. And that is, did I answer the question? It says find the rate of change of the area. Yep, that would be it. That's the rate of change of the area. So the area is currently getting smaller right there. Now the question doesn't ask for that, but that is what it means in this context.